Well, this next short section I want to go through on distributed forces is to just understand that loads due to weight always act through the center of gravity downward. In other words, if there's a distributed load, there is a CG, and it acts through that CG straight down. If the load was up at an angle, it'd still have a center of gravity which would act in that direction. However, loads due to pressure act in the direction of the arrows. And so here we have a little distributed pressure situation that is going in this direction. In other words, there's wind blowing along here, and the pressure acts in that direction. So let's solve this problem and see if we can find the moment about point O. Well, in this little problem, what we want to do is find the moment about point O. There is some pressure, some wind blowing against this triangular shaped sign. The sign also has some weight. So let's try to find the moment about O caused by those two distributed forces. First of all, let's talk about the pressure. So the pressure has some force due to pressure, which is caused by the pressure per square area times the area. So I'm going to say that there's a force P, which is equal to the pressure times the area. Okay, I'm given the pressure per area in pascals. Now, if you remember what a pascal is, it is a Newton per square meter, and that's equal to 150 pascals, newtons per square meter. If I can find the area of that sign, then I can find out the total pressure. So that is a triangular shaped sign, so that's going to be 1/2, and it looks like it is 1.2 meters on a side, and so I can get the total pressure here is equal to 108 newtons. Alright, where does that pressure act? Well, it acts in the direction of the arrows, and it's going to act in the centroid of that shape. The centroid of the shape, because it's a triangle, is going to be 1/3 from the big side of each side here. So anyway, it'll act right here where this dimension is 1/3 of 1.2, and it'll act right here where this dimension is 1/3 of 1.2. So right in there. So I'm going to go ahead and write those dimensions there. It'll be, this dimension will be 0.4, and this dimension here is also 0.4. Alright, how about the weight? The weight is 500 newtons, and because it is a distributed load, it also acts through the centroid, or the center of gravity. It'll act through the center of gravity, which happens to be in the centroid of that distributed load, which is in the centroid of the area. So I'm going to say that there's going to be 500 going this way, and this is 108 newtons going that way. Alright, now with that, we can use a variety of methods, but let's use our table method and see if we can come up with the moment about point O. So I have two forces. I have the pressure and the weight, and each of those are going to cause moment about the three axes. So what do we know? The pressure happens to be, there's the x-axis, the pressure happens to be parallel with the x-axis. About the y-axis, it has this lever arm. And so this is be 1 plus, this is 0.4 minus, or 1.2 minus 0.4, so that is that is 0.8. So it would be 1.8 up to that. So that would be 108 times 1.8, and let's see if it is positive or negative. It is trying to rotate it in this direction, so that would be, let me just go ahead and draw that on there. It'll be a rotation around that axis, so if we put that as our with our right hand rule, that'll be a negative. Alright, how about the pressure about the z-axis? About the z-axis, it looks like it goes in this direction, and here's the lever arm. It is 0.4 to the edge of the sign plus 0.1, because it's offset just a little bit. The diameter of the post there looks like it is 0.2, so that's going to be 0.5. And so I'll go ahead and put that in there, 108 times 0.5. Now is that positive or negative? Well, it's trying to rotate in this direction, so if you put your right-hand rule on that. That would show that that would be a negative. All right, how about the weight? The weight is parallel to the z-axis. It is going to be in line with the y-axis. In other words, it goes through the y-axis. And it does have some moment about the x-axis based on this 0.5. So let's go ahead and put all those in there. So it's going to be 500 times 0.5. It goes through the y-axis and is parallel to the z-axis. So I can find the moment about O by adding those up, and that's going to be equal to 250 y minus 194.4 j minus 5 or 54.0 k. And that's the moment about O using our scalar method, adding several forces together. It's pretty handy, I think. Well, in this second distributed load problem, I'm going to give this to you as a chapter 5 problem, but for right now, I just want to show you how to model the distributed loads. So on this top piece, this is a rectangular distributed load, so we know what to do with that. Over here on the side, the arrows are pointing in this direction. If the arrow is pointing in this direction, it is that force, or that distributed force, cannot be caused by gravity. It can't be a weight or something. It has to be some sort of a pressure or something in order for this to occur at an angle. The problem doesn't tell us what's causing that pressure, so we just have to take it like it is, like it's modeled, and say that the pressure is coming from that direction, and that's the way the resultant force would also be modeled. So let's go ahead and model these as two pieces. And we know a little bit about how to do this now. There's the centroid of the triangle-shaped load. We'll call that R1, and this will be the centroid of the rectangular load, and we'll call this R2. The lever arm, or the distance between point A and the resultant, would be 2 for this one, and it would be 3 for this one. In other words, this one is going to be half the total length here, and this one is 1/3 because that's 1/3 on that side. Next thing to just understand is when we sum the moments, if we do a moment about A caused by those two resultants, we're going to go positive in this direction, but it's going to, all we really have to take into account is we don't have to look at the components of these forces. We don't have to say here's a y component and an x component. If we do that, it tends to make the problem more complicated, and when we do this, what we're going to do is we're just going to say that the moment about point A, because this is now perpendicular to this inclined plane, I can say the moment about point A is just this r times this distance, and this r times this distance. So I'll just go ahead and write them down. This is just for these two forces, but I'm going to say the moment about A is going to be r1 times 2. Actually, those are both going in the negative direction, and r2 times 3. And we still may have some other moments caused by other forces or reactions or things like that, which we'll get to. But if we just look at the distributed forces, they'd look like that. So again, when you have an angled force like that, make it easy for yourself and just take, because it's perpendicular to the inclined plane, just take that force times that lever arm.